Hello. In this video, I'm going to be covering double integrals in polar coordinates and also double integrals over what I'm calling compound regions. And I'll explain what this means later. If you're watching very closely, you may have noticed that I've added compound regions to this video. It wasn't there previously in the overview, but it's going to be part of this video. Okay, so first of all, polar coordinates. Well, when we're doing double integrals, and the region that we're integrating over is a rectangle, it's quite natural to use Cartesian coordinates because in Cartesian coordinates a rectangle is simply described by x going between two limits and y going between two limits. However, if we want to integrate over different shapes, it may be more natural to use different coordinates that naturally parameterize these other shapes, other possible regions. And I'm going to cover in this class one other possible coordinate system that is natural to use when we want to integrate over disks. And these coordinates are called polar coordinates. You may have seen them before. The idea of polar coordinates is that we describe points in the plane by the angle that the point makes with the positive x-axis, which is theta here, and also the distance from the origin. And so in Cartesian coordinates, we describe the position of the point by the distance along the x-axis and the distance along the y-axis, labeled as x and y. But in polar coordinates, we use the angle, theta, and the distance from the origin, r. And so these two numbers, r and theta, are called the polar coordinates for the given point P. In order to describe a point, of course, the distance from the origin r will be greater than or equal to 0, and r equals 0 will correspond exactly with the origin. And the angle theta, made with the positive x-axis, is going to be greater than 0 and less than or equal to 2 pi corresponding with turning all the way around, the angle that goes all the way around and gets to the x-axis, approaches the x-axis from below. Okay, so using some trigonometry, you can derive the relationship between the Cartesian coordinates x and y and the polar coordinates fairly easily, and it's shown here. X is equal to r cosine theta, and y is equal to r sine theta. And so, when we want to do double integrals using polar coordinates, what we need to know is what is dA in terms of polar coordinates. So when we did integrals with respect to the Cartesian coordinates, we replaced dA by dx dy because the area of the rectangle, small element of area, is approximately delta x times delta y, the width times the height. But when we use polar coordinates, we have to reconsider this. The small element of area, described by a small change in the radius, r, and a small change in the angle, is going to be somewhat different than simply dr d theta. And that's because the arc length here is going to be r times d theta. As r gets larger, the actual arc length subtended by a given angle gets larger, and it depends on r in this way. And so this region, described by a small change in r and a small change in theta, has area approximately given by delta r times r delta theta. And if we translate this into an integral, that means that the dA that we're going to use in the integral becomes r dr d theta. So this r d theta is coming from the fact that we have r times delta theta here, and then the dr just comes from this delta r. And so when we do integration in polar coordinates, we replace the area element dA by r dr d theta. All right, let's look at an example of doing a double integral using polar coordinates. We're going to find the integral of this function, x squared plus y squared, over the unit disk. So polar coordinates are natural to use to describe a disk, which is the region inside the unit circle. So we want to do a double integral of this function, which is given x squared plus y squared. And the region R we want to integrate over is the unit disk. So let me just draw the unit disk in the xy plane. And the unit disk is the region of the set of points that have distance less than or equal to 1 from the origin. All right, and so this is the unit disk. You can also write it more explicitly as the set of points described by the coordinates x and y such that x squared plus y squared is less than or equal to 1. So the distance from the origin is less than or equal to 1. So when we want to do this integral in polar coordinates, we have to know how x and y are defined in polar coordinates, and then also what happens to dA when we change to polar coordinates. So we've gone over these in the previous few slides. Let me go back so you can remember. So first of all, we have that x is r cosine theta when we use polar coordinates, and y is equal to r sine theta. And the function we're integrating here is x squared plus y squared. So if we figure out what x squared plus y squared is, x is r squared cosine theta, y is r squared sine squared theta. This cosine should be squared, of course. And so we can factor out the r squared here, and then you have cosine plus sine squared, cosine squared plus sine squared, and that equals 1 by the Pythagorean identity. So x squared plus y squared is equal to r squared when we change to polar coordinates. And the dA is going to become r dr d theta, as discussed on this slide. So note here that the dA changes to r dr d theta. So this double integral, when we do it in polar coordinates, becomes the double integral of r squared r dr d theta. Okay, so now we can do the integral in polar coordinates by converting it to an iterated integral, just like we did with the Cartesian coordinates. We can integrate either with respect to r first or with respect to theta. So let's do the integral with respect to r first. So this double integral, I'll write the integral signs and the integrand. So the r squared times r becomes r cubed, of course. The inner integral will be with respect to r, and then the outer integral will be d theta. And we have to think about what the limits should be when we use polar coordinates to describe the unit disk. And so the unit disk is all the points that are distance less than or equal to 1 from the origin. So that means the distance from the origin goes from 0 at the origin out to 1 at the boundary of the unit disk. Now r goes from 0 to 1. And the angle theta goes all the way from 0 to 2 pi because it's the entire unit disk. We take all of the angles from 0 to 2 pi. So these are the limits that we need to use when we do the integral with respect to polar coordinates. Okay, and so now it's simply some one-dimensional integrals that we know how to do. We have the integral from 0 to 2 pi theta, and then we take the indefinite integral of r cubed, which is r to the 4th divided by 4, is evaluated from r equals 0 to r equals 1 d theta. And we get, when we plug in r equal 1, we get 1/4. And when we plug in r equals 0, you get 0. So this is 1/4 integrated from 0 to 2 pi, and that's just a constant integrated over an interval from 0 to 2 pi, so that will be a constant times 2 pi, the length of the interval. And so it's 2 pi divided by 4, or pi over 2. So this integral over the unit disk using polar coordinates gives us pi over 2. Okay, so I'm going to continue and do another example of doing an integral with respect to polar coordinates, or by using polar coordinates. And in this case, we'll do a double integral in order to find the volume of the sphere of radius 1. And so let's think about how we can set this up, first of all, as a double integral. So let me first draw the unit sphere and set the problem up. So we have our three-dimensional axes. This is the x, y, and z axis. And in order to represent the unit sphere, let me first draw a circle, attempt to draw a circle in the xy plane. And then a circle in the YZ plane. So this is the unit sphere, the set of points that are distance 1 or less from the origin. We might call it the unit ball also. And if we have a point that's on the boundary of the unit ball, or unit sphere, this point would have some given coordinates, x, y, and z, Cartesian coordinates. And because this point will be distance 1 from the origin, by the Pythagorean theorem, we have to have the x squared plus y squared plus z squared equals 1. Now, if we want to calculate the volume of the top half of the unit sphere, when we slice it with the xy plane, what we want to calculate is the volume above the unit disk in the xy plane and below the top of the unit sphere. And so in order to find the formula for the top of the unit sphere, we solve for z in terms of x and y. So if we solve this equation for z in terms of x and y, we get z equals plus or minus square root of 1 minus x squared minus y squared. And so when we use a plus, we get the top half of the unit sphere. When we use minus, we get the bottom half. And if we integrate this formula when we use the plus sign over the unit disk, then we're going to get the volume of the top half of the unit sphere. So volume of the top half is equal to the double integral over the unit disk, which I'll call R, of square root 1 minus x squared minus y squared dA. And R here is the unit disk. Okay, so since we're integrating over the unit disk, just like in the last example, it's very natural to use polar coordinates. And actually, polar coordinates are natural for another reason here, which is that this minus x squared minus y squared is going to be minus r squared, similar to in the last example where we had x squared plus y squared in the integrand. So if we use polar coordinates, then we're going to have minus x squared minus y squared equals r squared. That's what's here. And the dA, when we use polar coordinates, as we've discussed, is r dr d theta. So if we convert this integral, this double integral, into polar coordinates, we have the double integral over the unit disk of the square root of 1 minus r squared r dr d theta. So this is now a double integral expressed in polar coordinates. Now, in order to evaluate this double integral, we're going to convert it to iterated integral where we integrate with respect to either r or theta first. I'll do r first here, but you can do it either way. It doesn't make too much difference in this case. So let's convert it to an iterated integral. And the region r is the same as in the previous example, so the limits in the integrals will be the same. So our outer integral will be with respect to theta, goes from 0 to 2 pi. Our inner integral is going to be with respect to r, goes from 0 to 1. And we have 1 minus r squared r dr. It's just the same integrand, d theta. And we're going to do the integration with respect to r first, which is just a one-dimensional integral which we know how to do. So you can do substitution here in order to find the indefinite integral. If you do the substitution u equal 1 minus r squared, you'll be able to do this one. I'm not going to go through the details of doing that substitution. But when we do, we get that the indefinite integral is negative 1 minus r squared to the 3/2 divided by 3, evaluated from 0 to 1. If you don't believe me, you can check by taking the derivative. When you take the derivative of this, you have to use the chain rule. So you get 3/2 times 1 minus r squared times negative 2r. The 3 here cancels with the 3 here, and then the 2 coming from differentiating r squared cancels with the 1/2 coming from the 3/2 in the exponent. Okay, so now we plug in the limits. When r equals 1, we'll have 1 minus 1 squared, so 0. When r equals 0, we'll have 1 minus 0. Raised to the 3/2 is just 1, so we just have 1/3. And then negative 1/3 is just 1/3. So this becomes the integral from 0 to 2 pi of 1/3 d theta. And this is the integral of a constant over an interval, and so that is the width of the interval, 2 pi times the constant 1/3. 2 pi divided by 3. This is the volume of the top half of the unit sphere, or unit ball. But we wanted the volume of the entire sphere, the top half and the bottom half, and so we multiply this by 2 in order to have the volume of the entire sphere, which will be 4 pi over 3. And it's just 2 pi over 3 multiplied by 2, so 4 pi over 3. Okay, this gives us the volume of the sphere, and we found it by evaluating a double integral using polar coordinates. Alright, there's one other topic to cover in this video, which is doing double integrals over compound regions. And by a compound region, I mean a region which is made up of more than one rectangle. So we've covered doing double integrals over rectangles, did several examples. But what if we have more than one rectangle, a region which is made up as the union of more than one rectangle? So for example, what's shown here is one possibility. There's different ways you could write this as a union of two rectangles. But when we want to do the double integral over this region, we have to split it up into some union of rectangles. So for example, we could do it like this. We can split up this region into rectangle R1 and rectangle R2. And then the double integral over the entire compound region is simply the sum of the double integrals over each of the subregions. So I'll do an example of this. So we have a region similar to what I showed on the previous slide, and we want to do a double integral over this compound region. All right, so the region is shown there. We have to split up the region into two sections. We can do it as shown here, just as in the previous slide. We have the region R1 and the region R2. And the double integral over the entire region, which is the union of R1 and R2, is going to be the double integral over R1 plus the double integral over R2. So we want to take the double integral of x times y dA over R, and this is equal to the double integral over R1 of x times y dA plus the double integral over R2 of x times y dA. Alright, so now it is simply a case of calculating the two double integrals over rectangles, which is similar to problems we've done in the past. But I'll go through this in order to get a little bit more practice in. So let's convert both of these into iterated integrals. So the first one over R1. Let's do the integrals with respect to x first, and be alphabetical. So the inner integral is with respect to x, outer integral is with respect to y. And so we need to know what are the limits for this double integral when we convert it to an iterated integral. And this one is over R1. So R1 goes from 0 to 1. X goes from 0 to 1. So the limits for x are 0 and 1. And for R1, y goes from 0 to 2. And so the limits for y are 0 and 2. So this first integral, double integral over R1 becomes this iterated integral. And the second integral, oops, sorry, I forgot to put 2 here. This is the double integral over R2. The second integral will also become an iterated integral. Let's also do it with respect to x first. And we need to fill in the limits for the two integrals. And so when we integrate over R2, x goes from 1 to 2, and y goes from 1 to 1. Sorry, 0 to 1. Y starts at 0. 0 to 1. Okay, so now it's all set up as iterated integrals, and we just have to do a bunch of fairly simple one-dimensional integrals in order to finish the problem. So this first one, well, we still have the integral from 0 to 2. We need to find the indefinite integral with respect to x here, which is x squared over 2 times y. And this is evaluated from x equals 0 to x equal 1. And in the second iterated integral, we still have the integral from 0 to 1. The indefinite integral here is, well, the same as in the other one, x squared over 2 times y, evaluated from x equal 1 to x equal 2. So the difference here is that the limits in this iterated integral are from 1 to 2 for x, whereas here is from 0 to 1. And dy. Okay, so now let's put in the limits in both of these. We have this integral from 0 to 2. So we put in x equals 0, you get 0. You put in x equal 1, you just get 1/2 of, so this is y over 2. We have the second integral from 0 to 1. We put in x equal 2, we get 4 halves. We put in x equal 1, we get 1/2, and so when you subtract them, you have 3 halves. 3 halves y dy. And so we do these integrals. The indefinite integral here is y squared divided by 4. Evaluate from 0 to 2. This one is 3y squared divided by 4. Evaluate from 0 to 1. All right, and finally, we just plug in the 2 and the 1. And so when we plug in 2 here, we get 4 divided by 4, so 1. When we plug in 1 here, we get 3/4. And 1 plus 3/4, that would be 1.75. So this double integral is 1.75. Okay, so that's the example using compound regions. And this is the end of this video. In the next video, we're going to move on to a different type of integral called a line integral, which still involves integrating a function of two variables, but this time over a line rather than over a region, as in a double integral.